you. Okay, thank you, Sifan's invitation and introduction. It's my honor to present at the online seminar on Monte Carlo methods. This talk is about important sampling in Bayesian inverse problems using Quasi-Monte Carlo methods. Here is the schedules. In the first part, I will give some background on the methods and the problems, and then I will show some main results and numerical examples. Finally, I will show some conclusions. In recent years, Bayesian inference has become a key method for solving inverse problems and quantity. In UQ, it used the Bayesian formula to update the prior distribution of unknown parameters based on noisy observed data, thereby enhancing the modeling training. Now consider the problems of inferring the parameter Z from the observation Y here. The model is represented as this form. This is the forward models. The G is the responder operators. It maps the parameter to the PDE solvers and then to the observation Y here. There is a noise actor in the model. We assume the noise is a Gaussian noise, which is unobservable in practice. We will take pi0 be the prior methods. In this talk, I will focus on the Gaussian prior for Z, the parameter. Our goal is to estimate the posterior mean pi f. Here, pi is the posterior, which is proportional to the prior times the likelihood p. As we can see, the implied constant is usually intractable for some practical problems. All those Monte Carlo methods and the intentions are fundamental in Bayesian inference. They cause some challenges, particularly when dealing with the concentrate posterior methods due to the large data set or small noise levels. Now we assume the noise in the formal model has a covariance like this, which is proportional to 1 over n here. Here n denotes the noise level. Okay. A larger n indicates low intensity noise in the problem, which will lead to reduced uncertainties in the model. As we can see, due to the concentration effect of the posterior methods, planned Monte Carlo sampling based on the prior distribution may be inefficiencies for large n's. For example, if we want to estimate the estimation posterior means pi f here, we can take the parallel to do the samplings, we can use the planned Monte Carlo ratio estimator here. However, the prior method may be far from the posterior if the noise level n is very big. So our question is how to estimate the posterior means pi f efficiently as the noise level n goes to infinity. So the solution may be to use important sampling and Quasi-Monte Carlo methods to accelerate the rate of convergences. Here are some notation here. This notation is it denote the weight. The weight norms in the following slides like this. So if because we are using the Gaussian noise, so the likelihood can be expressed as this form here, using this notation here. So for simplicity, we use this notation for this node here. So we can have the Monte Carlo ratio estimator like this form here. So basically, we can just need to estimate this form for f, for general function f. If we take f be the constant 1, so we can get this form. So we will focus on this form in the following slides. Okay, we will use impedance sampling to address the challenges. Impedance sampling effectively reweights the sampling process to focus on the most critical regions of the parameter space. We take the QX be the proposal for the impedance samplings, so the integration can be expressed as an expression with respect to the Q, the proposal here. So we have a weight function Wx here. Now, particularly we take a specific form Q as the Gaussian distribution like this with the mean mu and covariant matrix sigma here. So the weight function or likelihood ratio can be expressed like this form here. So we can change the Gaussian distribution from unit standard Gaussian here, Z here. So the problem can be expressed as an expectation of with respect to the standard Gaussian distribution Z here. Now Z is the standard Gaussian here. So the function is G is Z here. Okay. If we use the notation tilde, the input is X. X is the proposal distribution here. So Z is the standard Gaussian. Now the L be the square root of the covariant matrix of matrix sigma here. So this is our function here. Fine. The big precise n here is to immerse the big precise x here and this in the ratio, like a ratio here. So this function we denote by the big precise n here. So also for yes, is our target function here. There are some candidates for impedance sampling proposal here. The simplest way is to use the prior as the impedance sampling proposal. That is, we choose the mu to the mu 0 and sigma to the sigma 0. As we can see, the optimal impedance sampling density for Monte Carlo methods is like these forms. But this optimal impedance sampling it is intractable, so we can calculate the implied constant here. So we will not use in practice. Actually, in this talk, we will focus on two important sampling proposals here. The first one is called optimal drip impedance sampling, ODIS. We use the mu to be the mu star and sigma to be the sigma yellow, the prime covariant. The mu star is the mode of the likelihood here, the mode of the likelihood yes. The other one is like Laplace based impedance sampling. So the mu will be the mu star here, and the covariant matrix sigma will be n-2 times sigma star. Sigma star is the inverse of the Hessian matrix of these functions. So actually, in the Laplace impedance sampling, we took the second order Taylor expression of the log likelihood. We should remark that the Laplace impedance sampling depends on the noise level and here, but this is not for the ODIS because the sigma here is not related to the noise level and here, but they have the same mu. Now we can consider a general problem of numerical integration for the function g and the density phi here. we assume that the phi is the density is IID, the Z is IID. So we can have the integration of this. The integrand domain is in dimension X. To use QMC, we have to map the domain to the unit Q here. So we use the contail function of the distribution. The capital phi here, inverse capital phi here is the contail function of phi here. So if we have this form, we can use the input from the unit Q to take the average to estimate the integral here. So in Monte Carlo methods, the input UK is random uniforms. For QMC method, Quasi-Monte Carlo methods, the UK is the low discrepancy points, which is deterministic. As is already noted, for QMC method, we can have a better rate of faster rate of convergences. Maybe the rate may close to 1/n, which is better than the Monte Carlo rate here. There are two main strengths of QMC methods in the literature. The first one is digital net. The second one is lattice rules. For more detail, I will refer to this reference here. There are some application of Quasi-Monte Carlo to UQ here. This paper is a surface of the application of QMC to equate PDEs with random diffusion coefficients. Under certain conditions, using Quasi-Monte Carlo can get a better rate of convergences, which is independent of the dimension. If the function in a wave space function space. And now this paper is used Quasi-Monte Carlo and multi-level Monte Carlo for eclipse inverse problems. In this paper, the authors took the price as the sampling proposal. So this paper didn't discuss the important sampling. And this paper look at the noise level robustness for the Laplace-based operations QMC estimator, which is very related to this talk. But this paper is not to use the QMC combined with important sampling. There are also many other papers about this topic. I just name a few here. Here are some brief introduction to lattice rule. In this talk, we use lattice rule, the main strength of QMC methods. The lattice rule points use this form here. This form here is the brace. It denotes the taking fractional part of each component here, and K is the index. N is a given sample size here, and the delta is a random shift. If we use a randomized Quasi-Monte Carlo methods, is very helpful for error estimation here. So the key for this the key question for lattice rules is how to choose the generating vector Z star here. There are some ways to choose the generating vectors. The usual one is to use the CBC construction. CBC is denoted for component by component construction. First, we can fix the Z1 to 1 and secondly, with the Z1 and ZD minus 1 fixed and choose ZD to minimize the error greater in dimension D here. So this is no Isotop's search because Isotop's search is practical impossible here. So also with the CBC construction, the optimal ways of convergence rates, optimal ways of convergence like this can be found for some weight separation space. The cost of fast SBC can be is of order the dimension x times the sample size n and log n. Use the fast Fourier transformation by this proposed by this paper. Here is the error analysis for the unbounded domains, because in this word we will consider unbounded domain here. So the worst case error bound for the integration here can be bound by this content times the norms of G, the integrand. The G is denote the norms for the weight separation phase is defined by these ones. The norms it depends on some factors. The first one is the weight gamma u here, which measure the importance levels of variables Zi. The second one is the weight function psi u here, the function psi u here, which reflects the growth properties of the function here. For these norms, a CBC error bound can be found for general weights here. Convergence rate depends on the relationship between the density phi and the weight function psi here. So if we can see the randomized QMC, we can get a Loomis square error here. The Loomis square error is bounded by the norm times this constants. If the norm is finite, so the rate is depends on these constants, these formulas here. So we refer to this paper for the detail on the error analysis for unbounded domain here. So here's the results from this paper. If the norm is finite and this function is bounded by this rate, the rate is r, then there is this generating vector Z thing which can be constructed by a CBC algorithm such that the Loomis square error is bounded by this one. The rate depends on this. This function is zeta function, which is almost 1 over n for this term. 1 over n. Okay. This function is denoted by the overall functions. So to use this series, we have to choose a proposed density and the proposed function weight function psi here. Now we consider the density of standard Gaussian. So the psi function here is the standard Gaussian density, and then this function is choose to be this function. This is the function. If we choose this pair, we can see that rates r can be 1 minus 1 over alpha here. Alpha is greater than 2. So use this value in the series, we can obtain Loomis square error is order n to minus 1 plus 1 over alpha plus epsilon. Epsilon is absolutely small constants here. So if the norm is finite for any alpha, we can get a rate of almost 1 over n here. If alpha is this is whole for any alpha here. So the rate, if this is no truth, the rates depend on the value of alpha. The bigger alpha is the better. Okay. So the question is how to verify the condition on the norm here. To verify this condition, we need some assumption for the integrands. We use the boundary condition for the integrand G here. The boundary condition is to assume that there exists a constant m such that the partial derivative is bounded by this constant. This constant m time is exponential to m times the norms z of z square. This boundary condition is a simplified version of Owen's boundary condition, which is expressed as a function of unit q. But now the z is in the unbounded domain. Is not in the unit q here. So it's this condition is easy to verify. Then this one for some practical problem. It usually holds for some function in practice here. Okay. We call the m as the rate of the boundary condition. So we can have a result here. If the integrand satisfy the boundary condition with the rate m is less than 1/4, when the density is the standard Gaussian, the Loomis square error of lattice roots for the integration is of order m to -1 plus 2 times m plus epsilon. So the m is the smaller is the better. So if m is absolutely smaller, positive constants, then we can get a Loomis square error rate of order almost 1/n for the lattice root. For example, if for this function g z of z, like this form, we can see that m can be a positive constant absolutely small. So we can, for this function, we can get a Loomis square error rate of 1/n here. Actually, under the same boundary condition, my recent paper with Zhen and Wang obtained the same error rate for scrambled net, another kind of RQMC methods. The second is about the main result. Recall that for our Bayesian inverse problems, our target function is like this form, g tilde like this form. X is like this form. So to transform to the standard Gaussian, we will use this function g. G is a function of z. Z is standard Gaussians. Okay. So the function big precise n here is take this form here. Take this form here. This is related to the long likelihood. This term. This is related to the likelihood ratio of wave function for these two terms. So how to calculate the norms for this target function here? It depends on some factors. The first one is the integrand f, f. The second one is the response operation g, or the big precise here. The third one is the proposal, depend upon the proposal, the parameter of the proposal, like the mean and the covariance, the square root of covariance. And the last one is the noise level n, depend on these factors. Now we are able to calculate the mixed derivative if we want to bound the norm. So here are some notations. Let A be a multiple index. So we can take the mixed derivative denoted by this form here. Let this notation be the vector with the entry 1 in the i's members and the 0 at y's. So by the Fadi-Bruno formulas, we can calculate the mixed derivative of the target function here, which can be of be a sum of these terms here. So this is the elements of the L, which is bounded. So this derivative can be bounded by distance. So actually the problem reduced to bound the derivative of g tilde here, g tilde of x for multi-index A here. So the question is how to bound this derivative. So recall that this is the g tilde here. Also, by using the chain rule, we can see that the derivative can be a sum of these terms. So the first one is the derivative of f and f here, and the second one is the derivative of big psi n here, and the third one is this term. Keep this term here. So to bound this one, this derivative, we have to bound these three terms. The first one, second one, the third one. So in the next, we are going to see how to bound these three terms here. If this three term is bounded, we can bound this derivative. So to bound the two quantities, we need some assumption here. The assumption one, for the function f, we assume that the derivative is bounded by this constant. It's just like the boundary condition in the last slides. So the range is MF. We particularly assume that MF is an arbitrarily small positive constant here. This is for this one. This assumption is usually holds for some function in practice. For example, if f is if we are going to estimate the posterior mean variance, so f x will be x or x squared. So this condition holds for absolutely small range MF here. The second assumption is about the big psi x, like this term, big psi x. Big psi x is in big psi is in this. Is related to the negative long likelihood. We assume the same condition for this function here with the range m psi for absolute small rate here. If this is a whole, then as we can see, for this two term is also bounded by this term. So if this holds, this relationship also holds for psi n here, because it's just quadratic. This term is also quadratic, so it's bounded by this terms. So we just need to need a condition for the big psi x. So if I think these two condition can be verified for practical problems. The third assumption here is is not easy to verify for some practical problem, but it's very critical in our analysis. Let mu star be the global minimizer of this function, and assume that the minimize this one is be 0. So if no 0, we can replace the psi x by psi x minus the minimize. So we can take the sigma star be the inverse of the Hessian matrix. And we assume that there is a constant delta between 0 and 1, such that the psi x is larger than this term. There is a constant sigma here, the delta here. So this assumption is used to assume a lower bound for this. If we have a lower bound this, so we can have a upper bound for the this term. Upper bound, because we want to bound this term, so we need a lower bound for this, so we can get an upper bound for this. Upper bound for this. As we can see for assumption 3, assumption 3 is naturally hold for if we take delta be zero because this term is non-negative. So if we don't consider the assumption 3, we can just take the delta be 0 here. Okay. This is the 3. This is the 3 key assumption in our analysis. Under these 3 assumptions, put them together, we can bound the derivative here. The derivative can be bound by this term, this formula here, because we have an upper bound here, and this is a bound put them here. Okay. This term is due to by these 2 assumptions here, so we can bound the derivative. Take the derivative, put the derivative in the norm. Sorry. So we can bound the norm here. So the norm is can bounded by the integration here. It's an integration about its exp to power this very complicated formula here. But this terms is on as we can see is just contracted. So we want this integral to be finite. So how to choose the mu and sigma to make this finite? This is the problems. Also, we have since the MF and quasi are absolute smalls, to make sure the norm is finite, if we just need to ensure this matrix is negative definite. This matrix is come from this one and this one and this one and this one. The merge the 4 terms together to get a matrix here. If the matrix is negative definite, so the integral is finite here. So the problem is to check whether this matrix is negative definite. For the price important sampling and ODIX, we take the sigma be the prior covariant matrix sigma 0 here. So put this inequality into this one, we can see A will be this term, which is always negative definite for any alpha and any n here. So we can have a Roomy square error of almost 1 over n here. For Laplace important sampling, we take a sigma be this form. So A will be like this form. If this factor is negative, then the matrix A will be negative definite. So it just requires that 1 minus 1 over alpha is larger than 1 over 2 and less than delta, and delta is no smaller than 1. So if this hold, we can get a Roomy square error of n almost n2 minus delta. Okay, delta. So as we can see, the larger delta, the faster rate is expected. So if the rate would make it depend on the delta. The larger delta is the better. For the last one, we propose a new important sampling. We take the covariant matrix and it's no this form, but it's divided by the delta here. If we put this if we put this one into A, we can get A be this one. So the matrix A is always negative definite for any alpha and any n. So we can get the optimal Roomy square error rate here, almost 1 over n. So I think this is a better choice than the Laplace important sample here to make sure A is always better for any alpha. So we can have the best rate here. I will show two examples here. The first example is a linear mapping with a small nonlinear perturbation. The response operator G here is a linear mapping with a small nonlinear perturbator, like this form. A is a matrix, so this is a linear part. The second is the nonlinear part, but it is very small because if we can take a small value of tau, we can get a small nonlinear part here. By the proof of by the result of this paper, we can prove that the precise z of z function has a lower bound here if it's under some condition. So for this example, assumption 3 is verified for this model. For this model here. For the assumption 2, as we can see, if the nonlinear part F satisfies the boundary condition with absolute small rate, then we can prove that precise of z satisfies the boundary condition with absolute small rate, assumption 1. So it's very easy to check the condition for the precise z of z here. The key is if we can verify the nonlinear part is satisfied the assumption 2, we can get the same condition for this function. The second one is elliptic PDEs. This is a standard model in UQ. Standard model in UQ takes this form here. This form here is the random coefficient here. Here the random coefficient we use the truncated versions. So the number of inputs is x. So dimension is x. We use a truncated here. So the response operator is G. If we get the PDE solution, we will use operation operator H. We will assume that H is a linear functional of the solution in the analysis. The Tataki function is also a linear functional of the solution P. Solution P here. So by the result in this paper, we can bound the derivative, and then we can have the derivative of the integrand here. Is bounded by this constant, this formula, which is bounded by this constant for absolutely small constant MF here. So the assumption 1 is verified for this model. For this function, precise of z is no function or is no linear function of p because it's square here. However, the derivative of precise of z is a linear combination of the terms of the form this of this. If this satisfies the assumption a boundary condition, then we can prove that this term also satisfies the boundary condition. So as a result, this is the condition that the derivative of precise z is bounded by these terms, bounded by two terms, also bounded by two terms. So the assumption 2 is verified. However, for this model, we are not able to verify the assumption 3 here. We can find a lower bound here. So we can just take the delta be 0 for this model here. We don't have a positive delta for this model. Now how about the conjunction effect on the norm? Following the words of this paper, we can work out the norm with respect to the norms level n here. Now we consider the relative Loomis square error, RRMSE here, the Loomis square divided by the integral here. For this work, we can prove that the following results. The first one, for prior importance sampling or ODIS, the relative Loomis square error is bounded by this. This is the norm. This is not with respect to the noise level n here. This is the convergence rate with respect to the sample size. For Laplace importance sampling, the relative Loomis square error rate is a constant. It's almost a constant for the norm, but the rate is big here. For the new importance sampling, we have the constant norm with almost the optimal rate here. As we can see, Laplace importance sampling and new importance sampling enjoys the noise level robustness properties. This is the noise level robustness because as the dimension x goes up, is unfriendly for a larger n here. The rates of, however, compared to a new importance sampling and Laplace importance sampling, the rates of Laplace importance sampling depend on the value of delta. If the delta is small, we can get a worse rate for the Laplace importance sampling. Particularly, it also requires that delta is bigger than 1/2 to guarantee this rate. Then next, I will show some numerical results. The first one is about example 1. We take a specific nonlinear function here. This is a nonlinear function, nonlinear part. This is a linear part here. For simplicity, we assume that the gamma star is the identity matrix and observation is 0. So psi of z, the function psi of z can be expressed as this form. It can be displayed by this form here. So it's easy to see that the 0 is the global minimizer of this function. The Hessian matrix, we can calculate the Hessian matrix as this form. So we can calculate the delta, the sigma star by this terms. As we can see, this psi of z has a lower bound, 1/2 the norm square. So to satisfy the condition we require in the assumption 3, so we just need to take the delta be 1/1 plus tau square. If we take the delta be this one, so this will be 1/2. So this is whole. So for this model, we just need to take the delta as 1/1 plus tau square. In our experiments, we will take a smaller delta and a larger delta. A smaller delta is 1/3. The larger delta is 3/4. 1/4, 3/4. The dimension x is 8. We take the Gaussian prior, the mu 0 is 1. The sigma 0 is the the elements of mass of the index A, I, and J. We consider for a Gaussian proposal for importance sampling here. This is the prior importance sampling, ODIS, Laplace importance sampling, and new importance sampling here, as we can see. Okay, the test function is about the norm of the parameter, the norm of the parameter. So for this problem, the assumption 1 to 3 holds. Okay, I will show the Loomis square error, which is scaled by a factor of n to x minus over 2 to minimize the relative Loomis square error. Here the result. This picture is about the relationship between the Loomis square error with the normal levels for the problem. The 3 importance sampling for Monte Carlo and randomized Quasi-Monte Carlo or lattice rule Monte Carlo. Quasi-Monte Carlo methods. As we can see, as as the noise level n goes up, the rule mean square error keep the same, almost keep the same for the Laplace important sampling, the yellow one, and the new important sampling, because these two methods is noise level robustness. This is known for the prior important sampling and ODSI important sampling because it goes up for as n goes up. Particularly for larger delta goes up quickly than delta 1/4. Okay, so as we can see that this property is very robustness to the noise level. So let me show you some the convergence rate with respect to the sample size n. As we can see, for the RQMC method, the new important sampling and Laplace important sampling converge faster than ODS and price important sampling here. So we have some the conclusion is the new important sampling perform the best. The Laplace important sampling gains a faster rate for larger delta. As we have shown that for larger delta we can get a faster rate for Laplace important sampling here. The next, this picture is about the large noise and small delta. We take the noise level and is 20. This is it has the effect of large noise. So for this setting, the posterior is very far from the normalities. Very far from the normalities. So as we can see, for this setting, the Laplace important sampling performs much worse than other methods, because for this delta is smaller than 1/2, and the posterior is far from normality. So Laplace is not a good choice for QMC. So the conclusion is that it's risky to use Laplace important sampling QMC if the posterior is far from the normality here. The second is that here is the second example, elliptic PDE. We can see the result here. Okay, the dimension of for this problem is 8. The observation is taken at this point here. The physical domain is 0 to 1 is 1 dimension. For this model, assumption 1 to 2 holes is satisfied, but assumption 3 is satisfied for delta equals 0. Here are some results. We can see. We also compare the another type of proposal, T proposal. We also compare the result of T proposal. So this method is for the T distribution-based Laplace important sampling. It just replaces the Gaussian by the T distribution. Okay, as we can see before, these two methods is robustness. The Laplace important sampling and T important sampling robustness is related to the noise level. As we can see, the T important sampling converges faster than the Laplace important sampling for this one. So we should suggest to use T instead of Gaussian for Laplace methods here. So you have a faster conversion. For this model, we are not able to use new important sampling because delta is 0. So the new important sampling can be used for this model. Finally, have some conclusions. We analyze some conversion results of important sampling combined with lattice rules and observe that choosing a proper important sampling density can ensure that functions lie in the space of which function we can observe an error rate of almost 1/n. Selecting a poor important sampling density can make the function unfriendly to QMC methods like Laplace important sampling in our numerical analysis and numerical results. We also propose an efficiency important sampling that not only enjoys the noise level robustness properties, but also has a fast rate of convergence. The proposed important sampling depends on prior information of the lower bound of the negative log likelihood. This condition may be very hard to verify for some models. However, this paper does not look deeply into the effects of dimensionality. The relation between the error rate and the dimensionality is no study in this work. To obtain the dimension-independent error rate bonds as the dimension x tends to infinity, one may select some special weights involved in the norm. Yeah. Okay. Thanks for your attention. I will thank Stefan and Guanyang for invitation and organizations. Thank you very much.